Today's problem is get minimum squares. Difficulty is medium. Given a positive integer n, find the minimum number of perfect squares, which would be a square of an integer that sum up to n. Note, every positive integer can be expressed as a sum of squares, since 1 is a perfect square. So, worst case, any number can be represented as 1 squared plus 1 squared plus 1 squared, etc. All right, these examples are, they're too simple, I think, to be useful. What if n is 100? How many perfect squares do you need to sum up to 100? Well, 10 times 10 is 100, so you need 1. What about 6? Okay, then you need 1 squared plus 1 squared plus 2 squared is 1 plus 1 plus 4 is 6. Three numbers. N is between 1 and 10 to the 4th. What is that? 10,000. Let's see. Expected complexities, O of square root of n. And auxiliary space, O of 1, constant auxiliary space, topic tags, dynamic programming, mathematical, recursion. I don't think recursion is going to work. We're going to start with recursion and then, kind of fine tune it. But really, there's a lot of ways to do this. Recursion is 1. Top-down dynamic programming is 1. Bottom-up dynamic programming is 1. Bottom-up with tabulation. There's another way to do the bottom-up dynamic programming, and that is to pre-compute all of the perfect squares that are less than or equal to n. Okay, we can do that. What else? A breadth first search would work. And then there's one more that we'll talk about at the end. I have to admit, my first thought on this, let me get a pen. My first thought on this was, what if you have a number like 43? Okay, so let's just take the biggest square that's less than 43. That would be 36. Okay, and then subtract it from 43. So now what we have left is 7. Biggest square less than 7 is 4. Subtract that, and that is 3. It's not a good number because, see, that's going to take 3 more square numbers, 1 squared 3 times. So that's 3, 4, 5. 5 operations. Yeah, so it turns out there's a better way to do this, and that is to identify the recursive nature of the problem, which is that we can form the sum m as x squared plus n minus x squared for various values of x, as long as x squared is less than or equal to n. So, min squares of, let's say, 43 would be the min of 1 plus min squares of n minus x squared for all the x squareds that are less than n. So we could try 1 plus min squares of 42. We could try 1 plus min squares of 39. That would be, using 2 squared. If we use 3 squared, 3 squared is actually the best way to do this. If we used 3 squared, that's 9. And that would take us down to 34. Okay. It took us 1 operation to do that. And then again, we have to make a recursive call to find out what is min squares of 34. Well, it could be 1 plus min squares of 33, 1 plus min squares of 30, 1 plus min squares of, yes, if we use 3 again here, subtract 9, and now we're down to 25. Okay, so that's good. It's going to take us one operation to subtract 9 from 34, and then this is a perfect square. So actually the answer is 3 for 43, not 25. So my initial thought is not going to work. Anyway, what we've set up here is the recursive version. So the base case is if you pass in a square number. Okay, so it's going to return min squares of a square number is 1. All right, so for n, if n is 1 or 2 or 3, we're just going to return n because it's going to take one square number to get to 1, 2 to get to 2, 3 to get to 3. It's just 1 squared, you know. Then we'll set count to n. That is worst case. All right, worst case, we can make any number just using 1 squared n times. So that's the worst. So let's start with that and then, you know, see if we can improve on it. We'll go from 1, I equals 1. Do we even need to do 1 here? I'm trying to think. Yeah, I guess we do. Yeah, okay. We're going to use all the numbers that where the square is less than n. And we're going to figure out what is 1 plus min squares of n minus I squared, and then return it. So, yeah, I mean, let's run this. I'm almost certain that it's going to time out. But yeah, let's try it. What? Whoa. Okay, that's good. Well, we got through 10 cases out of more than 1,000 before timing out. All right, so let's revise this a little bit, because the recursive case can be converted to dynamic programming. That is, we can memoize the computations. I mean, what we have is the two properties that we need for dynamic programming. One is called optimal substructure, meaning that we can compute the optimal solution for the problem by computing optimal solutions of subproblems. The subproblems in this case being min squares of n minus x squared. And if we find those, then we can find the minimum perfect squares that sum to the given number. And 2 is overlapping subproblems, meaning we're going to have to compute the same things over and over again, and we don't want to do that. Even a simple number like n equals 6, we're going to have to compute. So we would go through that and say, well, what about 6 minus 1 squared? Okay, so that's 5. What about 5? What about 5 minus 1 squared? So we got to compute the 1 squared twice. We also have to compute the 2 squared twice, because after we get from 5 to 4, we get the 2 squared, but we still have to compute from 6. We got to say, well, all right, so what if we subtract 2 squared from 6? All right, so we're just computing the same things over and over. All right, so I'm going to try to convert this from the recursive version to a top-down BP version, and I think what we can do here, I think we can use the memo array as, I think we can use that as a class variable. So I'll say private int memo. Okay. And then in min squares, we need to create the memo array. So we don't need that again though. Let's say memo equals new int n plus 1. All right, so that'll give us numbers from 0 to n. We don't need the 0, but we do need the n. Or indices from 0 to n, which we need the n. All right, and then arrays dot fill memo -1. I'm going to fill a memoization array with -1s as an indicator that if the number at a particular index is -1, we haven't computed that number yet. So we have to compute it. If it's not -1, we already computed it, and we can just use it without recomputing it again, and then we'll return something that we'll call min squares recursive and pass in the n. All right, how does that look so far? Private int memo, I think that's okay. So let's do this. Private, let's call this, it's going to return an int, min squares rec, the n comes in. We need that. We have the same base cases. Whoa, I don't want that. We have the same base cases if n is less than or equal to 3. We have a new case where if memo at n is not equal to -1, then we'll return memo. We already computed it. Oh, I don't need that. All right. What's next? Count equals n. We still need that. Everything else here, we still need that. The only difference being that we are memoizing the count. All right. Let's try just like a compile test on this. What does that say? Private int min squares rec. Okay, let me look at that for a second. Okay, sorry, this should be an int, and I noticed down here this needs to be changed. We want to recurse with the recursive function. So anyway, let's try compiling that. Yeah, I mean, the only thing that concerns me here as far as the top down is that, well, I mean, the numbers go up to, what, 10,000? A lot of recursive calls, but here, let's try it. Okay. Now, let me do one more thing here, and that is this O of square root of n. There's no way in anything that we've discussed that you're going to get an O of square root of n, because you're going to have to go through all the numbers from 1 to n, and then the processing for each of the numbers will be O of square root of n, but the overall time complexity would be O of n times the square root of n. There is a way to get a square root of n time complexity, and I might as well show you that, even though I don't think anyone would really expect you to come into an interview and do it. I mean, and obviously the dynamic programming works the recursion works as long as you memoize the results. And yeah, but let's look at it anyway. Okay, I just pasted the new code in here. This is where the mathematical topic tag comes into play, I guess. There's something called Lagrange's four-square theorem, which says that any there's only four possible solutions to this problem: 1, 2, 3, or 4. Okay, so case 1 is if the number is a perfect square, then the solution is 1. So we've got a helper function here, is square. So we'll take a number in x, we'll take the square root of x, that returns a double, so we'll just convert it to an int. If we can square that and get back to x, then it's a square. It's a perfect square. So the answer is 1. Second possibility is if second possibility, the number is the sum of two square numbers. How do we figure that out? Well, we pass in the number n, and we take the, as many numbers as we need to. As long as the square of I is less than or equal to n, we subtract the square from n, and then we see if the result is a square. And if it is, then the answer is 2. All right, now it gets a little bit tricky. Actually, let me pause this and write down the formula. Okay, here's the formula. 4 to the power of k times 8m plus 7. If you can express a number in that form, then it is going to take 4 squares, 4 perfect squares, to sum up to that number. Okay? Now, how do we figure that out? All right, so the first thing is this. We divide out all the powers of 4, and that is going to leave us with 8m plus 7. So if we mod the number by 8 and the remainder is 7, then we return 4. I mean, the other the other part of the formula here is if, and we've already gone through 1 and 2, so it's not a perfect square. It's not a sum of 2 squares. If the number is not in this format, then you need 3 perfect squares. Okay, so that's what this is. If we have looked at all of the other possibilities, none of them is true, then we're going to return 3, and this is actually O of square root of n. So let's try and submit this. Okay, so that covered a lot of ground, but yeah, go ahead and like the video if you liked it, and you can subscribe to the channel, subscribe to notifications, and we'll see you next time.